Hello, everybody. Welcome back. Today we're going to be looking at Unit 6.2, which is all about looking at a more visual representation of endothermic and exothermic processes called energy diagrams. And some of today will be a little bit of review. So let's get started. So we looked last time at what an endothermic and what an exothermic process really means. What are the definitions? Where does it apply? And now we're going to look at a more visual representation of that using an energy diagram, which we have actually seen before. If you'll notice, we're looking at this for a chemical reaction. We have potential energy on the y-axis. What would be on the x-axis would either say reaction progress or reaction coordinate, one of those two things. And what we have here is the reactants are right there. Okay, so the potential energy of the reactants is in this position. I'm going to mark that with an R on the y-axis. So that's the potential energy of the reactants. The products are down here, and I'm going to mark that approximate location on the y-axis with a P for products. And if you guys will recall from previous lessons, this distance from the reactants to the top of that hill, that is the activation energy, which gets us up to the, this is review, activated complex, if you'll remember that term, okay, which is just kind of a hybrid between reactants and products. What I care about on this graph today, however, is really more the distance between the reactants and the products. That is my delta H, my change in heat for this chemical reaction. Okay, so let's talk out a couple of things to notice here. This reaction is exothermic. How do I know that? Because the potential energy of the products is lower than the potential energy of the reactants. So that's one definition. Another definition of exothermic reactions. Let's review what exothermic means. That means that heat is leaving the system. In this case, the system is the chemical reaction itself. Heat is leaving the system. Where is it going? It's going into the surroundings. And you can see, guys, you'll very often see chemical reactions written with the word heat or a number of joules, that would be an amount of energy, on the product side. And if you see heat or energy on the product side, that's another way to indicate this is an exothermic reaction. Okay, now let me come back here and write this out a little differently. The change in heat for any reaction is always going to be the heat of the products minus the heat of the reactants. Final minus initial, products minus reactants. If you imagine what some of those numbers would be on the y-axis, if you do the potential energy, the heat of the products minus the heat of the reactants, I hope you'll understand that you will get a negative number there because it's a smaller number minus a larger number. And we saw in the last lesson that exothermic reactions will always have negative changes in heat. So put all of this together. These are all defining characteristics of an exothermic reaction. When you see a general downhill curve on an energy diagram, that's going to indicate an exothermic reaction. Heat is leaving the system. Okay. Let's look at an endothermic situation. Okay. We have the heat of the reactants relatively in that location. The heat of the products is higher Potential energy of the products this time is higher than the potential energy of the reactants. Heat is absorbed into this system. Okay, you can see that the word heat is now written on the reactant side. All right, and here is my delta H. Okay, and it's still going to be products minus reactants, but this time the products are higher. Products minus reactants, that's going to give me a positive answer. Okay, and we saw that in the last lesson, that endothermic reactions have positive delta H values. All right, so we're seeing this general uphill curve. That's indicative of an endothermic curve. Heat is flowing from the surroundings into the system. So let's look at a problem here. Okay, I'm going to introduce it to you, but then I want you to pause your video so that you can try it on your own. It says an experiment was performed to determine the energy changes in a chemical reaction. A graph of temperature versus time is shown. Please notice, guys, that is not a graph like the ones we just saw. That's not a graph of potential energy versus reaction progress. This is a different graph. This is just monitoring the temperature. Letter A says, is the reaction exo or endothermic? Justify your answer. B says, a student makes the following statement. Do you agree or disagree? The energy required to break the bonds in the reactants is less than the energy released when the bonds form in the products. And then part C says to sketch an energy profile. That's what we were just looking at for this reaction. So I want you to pause the video for just a second and see how you can do with this. All right, so as I said, guys, this graph that you're presented with, you need to be careful. That graph is not an energy profile. It's just showing how the temperature changes. And as I can see, the temperature went up. Let's remember from unit 6.1, if a reaction shows an increase in temperature, feels hot to your hand, that is an indication of an exothermic reaction. An increase in temperature, remember, you and the thermometer are part of the surroundings. An increase in temperature means the energy must be flowing from the system to the surroundings. The system is releasing heat. That is by definition exothermic. Now letter B is a little bit tricky, and if you feel confused by my answer to letter B, don't worry, we're going to cover this in more detail in a later unit, in a later subunit within Unit 6. So the statement says the energy required to break the bonds in the reactants is less than the energy released when the bonds form in the products. And that is a true statement, okay? So let me read you what I've written here, and then I'm going to show you something. I agree with the statement. Since the reaction is exothermic, that delta H value is negative. Remember from last lesson, Unit 6.1, when you break bonds, okay, in reactants, breaking bonds is an endothermic process. So those energies are going to be positive. When the bonds are formed on the product side, remember, free to form, those are exothermic, and those are going to be negative. If I add all of those energies together, that gives me the total delta H for the whole reaction. And as I saw from letter A, the reaction is exothermic. Again, if that is confusing to you, don't worry about it so much, because we are going to cover the energy of breaking bonds and forming bonds and how that correlates. We're going to cover that more in a later unit. Okay, if it makes sense to you, great. If not, don't worry. We're going to clear it up in a later subunit. But let's do this last part, sketch an energy profile diagram. We know that it's exothermic. So I'm going to draw a set of axes. Potential energy is on the Y. And I'm going to write reaction coordinate, which you could write reaction progress as well. And this doesn't have to be fancy, guys. You can simply draw something that looks like this. Okay, that indicates to the AP graders that you understand that the potential energy of the products is less than the potential energy of the reactants, and that is by definition an exothermic curve. So something like that. So I hope that gives you a little bit of a fuller picture of what it means for a process to be endo or exothermic. So I hope you've learned a little bit of something today, and I look forward to seeing you next time.